Hello and welcome. Today we will discuss support vector machines, and this is actually a correction video. I had already uploaded a video on support vector machines, but there was a minor mistake there, so I will rectify it, and also I will give an example of how a support vector machine draws the wide margin decision boundary. That example will be also demonstrated in this. Okay, so let's get started. So here, before we move into stats about vector machines, few preliminaries of linear algebra. So these are two vectors, a and b. So how do we draw the vector a minus b? So this is a minus b. Let's call it c. And as I had mentioned in my earlier videos, that uh, we usually draw the vectors from origin, but not necessarily a vector has to be from an origin. It's a direction and can be represented anywhere. However, for understanding, let's pull C to origin. And now if I have two vectors B and C, what is B plus C? Okay, so the A vector is actually B plus C. So you can put both the vectors end to end and join it. Like this is B and C, this is B plus C. Another concept is the concept of dot product and cosine similarity. So if we have two vectors A and B and the angle between them is theta, then the cos of that angle, cos theta, is actually the dot product of A and B divided by the norms of A and B multiplied. So A dot B by norm of A multiplied by norm of B. Okay, so we know that the theta 90 degree, cos theta is cos 90 degree is 0. In that case, the dot product is 0. So if we find, on the other hand, if we find the dot product to be 0, we know that the angle between them is 90 degree. And more the similarity between two vectors, the dot product will be higher. So if the dot product is 0, the two vectors are actually perpendicular to each other. Okay, and this is the concept of norm, that is the length of a vector, which is square root of the squares of its coordinates. So if a vector A has coordinates a1 and a2 in 2 dimension, it's square root of a1 square plus a2 square, and this can be this can be elaborated across the dimensions as we keep on adding dimensions. Okay, so now let's get into support vector machines. A quick recap of logistic regression. In logistic regression, we found out how we could draw a decision boundary between two classes or observations of two different classes, the red and the green classes, and we found the equation of the decision boundary line that can divide these two classes. That is W0 plus W1x plus W2x equals 0. However, it turns out that if the logistic regression can conclude at different lines, okay, not only one line based on your initialization or maybe based on the number of iterations, it can converge at different lines, and each of these lines can be a decision boundary actually. But which of these is the best decision boundary? Okay, so probably this one, the one in black. And why so? Because the closest points of opposite classes are at maximum distance for this decision boundary, and these points are called support vectors. Okay, so in support vector machine, we will find a mechanism using these support vectors so that we could maximize the distance between the points which are closest to the decision boundary, and accordingly we will find the best decision boundary. So they will have a wide margin boundary. So these blue lines show the margin, and there are no points within that boundary, within those margins. So if we can find a line which has a sufficient margin, that is possibly the best classifier. Okay, then there's no confusion about any point to which class it might belong. The more and more it comes closer to the line, there's some confusion. It might belong to the other class. Okay, so that is the motivation behind the support vector machines. Okay, so let's see how we can draw that. So this is the largest margin demonstrated in the diagram. Okay, so let's say we have these points. Okay, and let's say this is the best decision boundary, and it has two margins around it. So why is this the best decision boundary? It will create the widest margin with the support vectors. And what are the support vectors again? The points that are closest to the margin but belonging to opposite classes. Okay, so here in this one, these are the support vectors. Okay, so if we had this line as the best decision boundary, this would have been the support vectors. So let's see how we can find these support vectors, okay, mathematically. So let's say the equation of this decision boundary that we are trying to find is wx plus b equals 0, where x is x1 and x2 represented in 2 dimension here. Okay, and in that case the two margins would be wx plus b equals -1 and the wx plus b equals +1. Okay, they are equidistant from the decision boundary. Okay. So now let's consider these points on wx plus b equal to -1. Let's call this the minus line. The points on the minus line are x1 and x2, while the point on the plus line is x3. Okay, then we can write wx1 plus b equals -1, and we can write wx2 plus b equals -1, and we can subtract one equation from the other and put it in the form w and the dot product of w and x1 minus x2 is 0. Okay, so just remember these are actually dot products. Okay, so as an equation of the line can be represented in terms of the weight vectors and the dot product. Okay, plus b equals -1. Okay, so now what we conclude that w the dot product of w with x1 minus x2 is 0. So what can we say from here? That the w vector is perpendicular. If you remember our first slide, if the dot product is 0, then the two vectors are perpendicular. So w vector is perpendicular to x1 minus x2 vector, right? So by rules of vector subtraction, so what is x1 minus x2? Again, if we remember from our first slide, so this is let's see what is x1 minus x2. So this is x1, this is x2, and this is x1 minus x2 vector, right? So we can again this vector is drawn over here for better understanding. Let's represent it with respect to origin. Okay, so let's see now. Okay, so this is with respect to origin. Now w vector is perpendicular to this vector, this x1 minus x2 vector. So how does our w vector look? Let's see. Okay, and this vector is parallel to all the three lines, both the blue lines and the black line. Okay, and now let's see how the w vector looks. Okay, it's perpendicular to x1, so this red vector is now the w vector. Okay, and because it's parallel and because it's perpendicular to our x1 minus x2. Okay, now let's consider the distance between the two blue lines, that is the margin, this margin. Let's consider it to be L. Okay, so this is the width. L is the width of our support width, or the distance between the support vectors or the two margins of the actual decision boundary. Okay, so if that is the case, how can we create a vector for L, a vector which can represent L? So if we can drop a line, a perpendicular line from x1 to on the -1 line, a perpendicular from x1 on -1 line to the +1 line, then that is that the length of that vector would actually be L, right? And let us call that vector Z. Okay, and we can see that this vector is also perpendicular to both x1 minus x2, right? So let's pull it over again. So this Z vector, let's draw it from origin. So we can see that the Z vector will be some multiplier of the perpendicular of the weight vector. The weight vector can also have a length greater than the Z vector. In this example, however, it has a smaller length. However, we can represent the Z vector with some multiplier of the X vector, right? Sorry, of some multiplier of the W vector. Okay, and let's see. So let us consider that multiplier as lambda. Then we can say Z is lambda times W, right? Okay, and then the length of Z is actually the width of these two lines, the length of z. Okay, and how can we calculate the length of z? That is the norm of z. It is lambda times the norm of w, right? It's a direct interpretation of the previous formulas. And then let's consider the point where we have dropped the perpendicular from x1 on the +1 line as x4, and x4, since it's on the +1 line, should belong to the red. If there's a point over there, it should belong to this red classes, that is the positive classes. Let these be the positive classes and let this be the negative classes, or maybe reverse, let this be the negative classes or this be the positive class. Anyways, it belongs to the red class, a point over here. Okay, so what can we say about x4? x4 is also a vector, right? So we get an equation from here also. We get z in terms of x4 and x1. If you observe carefully, z is x4 minus x1. Okay, so now this will help us derive the length or the width of these two lines. So what do we have? We have z is lambda times w. So x4 minus x1, the vector x4 minus x1 is also lambda times w. Also we have w x1 plus b equals 1, because x1 is on this line, wx plus b. We then have w x4 plus b equals 1. Okay, wx1 plus b is minus 1, this equation, and x4 is on this line, so wx4 plus b equals 1. Okay, and then we can replace x4 by x1 plus lambda. You can check it here in this equation, right? So wx1 plus lambda w plus b equals 1, and then if you replace wx1 plus b by we know wx1 plus b is minus 1. If you replace that, you get this equation, and from there you get L. Sorry, this will be lambda. This will not be L. This will be lambda. Okay. This will be lambda. Okay. This is not L. Okay. So we get lambda equals 2 by w dot w, right? And then what is L? We know we have the equation of L, which is the norm of which is lambda times the norm of w dot w, right? We know L is lambda times the norm of w dot w. Here, lambda times w, then the length of L will be lambda times the norm of this, right? So we can find L, which is norm of z, is lambda times the norm of w, and from there we can get L is 2 by norm of w. Okay, so we get the width of the line in terms of the w vector, value of the w vector. Okay, so what we need to do, we need to maximize this. We need to find points in such a way that this L, or 2 by the norm of w, is maximized. And what is our constraint? Our constraints are wx1 plus b equals minus 1 and wx4 plus b equals 1. That is, if x1 and x4 are our support vectors, it should satisfy this condition. Okay, now let's see. So this was something we wanted to maximize, okay, which is equivalent to minimizing, just the reverse. Okay, so we are converting it into a minimization problem, and also we are combining the constraints. We will combine these two constraints now. Okay. How do we combine? We add a characteristic variable y, yi, and we convert x to xi. So if xi belongs to this plane, for red observations xi is 1. If xi belongs to the red observations, yi is 1, and if xi belongs to the other observations, the green observations, yi is minus 1. In this way we can combine these two equations into this single equation. Okay, so now this is our minimize. We will minimize this with this constraint. So let's see, this is our minimization problem with yi as a characteristic variable, and so we combine these two using a Lagrangian. So we will use the Lagrangian technique of minimization or optimization. And how do we combine both the equations? We add another Lagrangian variable. Okay, so alpha I is our Lagrangian variable, and we combine them into a single equation. Okay, now this is, we have to now minimize this one, L combined, that is we have combined both these two, this one and this one. Okay, combined into a single equation. Okay, now how do we do the minimization? Or we find the extreme points by taking the del L del W and del L del B separately, which gives us two more equations, that is alpha I yi xi, summation is 0, and if you do the partial derivative with respect to B, you would get summation of alpha I yi equals 0. Okay, and then if you replace these values in over here, you would get L combined as this, summation of alpha I minus half and summation of alpha I alpha j yi yj xi xj. I and j are the support indexes of the support vectors, in this case 1, 4 and 2. Okay, so what do we see? So here we have a minus sign, right? And xi xj is the dot product. So if the dot products, if two classes are similar, then the dot products are higher, right? So if we have higher dot products, and if yi and yj belong to opposite classes, that is one will be minus and one will be plus, then the product will be minus, right? And that minus, when added with this, combined with this, would become a plus. Okay, so plus, and this would be maximum when we have xi and xj are similar. So similar data points from opposite classes would boost this, and since this is a minimization problem, if this gets higher, so the minimization would be boosted. Okay, so we have to take similar classes from opposite, similar objects, but from opposite classes to do this optimization. Okay, that is the significance of this equation, which are again the support vectors. Because they are closest to the line, they will be similar, but they will belong to opposite classes. Okay, now let's see how that works. Okay, so let's consider a new set of points, and let's just assume, so here we have shown the similarity, okay, between these. So some are having high, these are the highest points of the opposite class having higher similarity. Okay, so this is some of the techniques you can use to select which points you would consider as support vectors. Okay, however, we would make it a bit simpler here. Suppose after observing all the points, we have considered these points as support vectors, though we need to look so that we don't take similar points from same class but similar points from opposite class. However, let's assume we have selected these as similar vectors. Okay, and y rate is -1. So what is the value of yi's? If it belongs to red class, this is -1, and if y observation belongs to the green class, it will be +1. Okay, that is how we will assign the values of y. Okay, and let's see how then this product turns out. So we will have to do a product, a combination. We will have to find these three for each of these x's, the dot product with each other, and also the y product with each other. So if we create a matrix, so let this be x1, this be x2, and this be x3. So these values yi yj, that is y1 1 2 x1 x2 y1 y1 x1 all these values are given by this matrix. Okay, and if we put these values over here and expand this, we would get some sort of equation. We will use this over here, and then also here we can use the values. Here, although we don't need the x's, we will just need the y's. We will get some equations. Okay, one is over here we get this equation, and from here we get alpha 1 plus alpha 2 equals alpha 3. So if we replace that alpha 3, so we get this equation over here. Okay, now again we take the partial derivative and equate it with 0, so we get the values of we get equations in terms of only alpha 1 and alpha 2, and if we solve them after doing the partial derivative, we get the values of alpha 1, alpha 2 and alpha 3. So this is just an indicative of how you can derive the values of alpha 1, alpha 2 and alpha 3. So you need to choose the correct support vectors, and if you choose the correct support vectors and properly derive the values of alpha 1, alpha 2 and alpha 3, you would get the weights as W. You can get the W values from here. After you get the alpha 1, alpha 2 and alpha 3, you would get the W values, and then you can use the W values and to derive the B value from this equation. You know the yi's, you know xi, you can choose any yi, any xi and derive the value of B. So this becomes our equation of the line. Okay, this W, W0, W1 and B. Okay, and so if we draw the line, if we plot the line, it appears like this, and we know what is the margin. The widest margin is 2 by norm of W. So if you calculate the norm of W and do 2 by norm of W, here you get this value, so which is the width between these two margins. So you can see it's approximately 4.12. Okay, so this is how support vector machine works. I hope this was intuitive in understanding. But support vector machines are mostly used for non-linear classifiers, though we can use the logistic regression by raising it to polynomial, but support vector machines are very effective in non-linear classification. So let's see how a support vector machine can be used for a non-linear classification. Okay, so there's a kernel trick that we do. So suppose these are our observations, and you can see the red and blue points are intertwined. We cannot draw a linear separation between them or a linear decision boundary. So what we can do, we can imagine some sort of complex equation of a boundary and transform it using a kernel trick to some linear equation, or we can think in another terms. We can think that we use some kernel function which helps us to find new features, which helps us to add new features to these observations. And new features means adding a new dimension, right? So if we use a kernel function to add a new dimension, then we see that in that new dimension these points are separable, right? Now you can see the red points and the blue points are now separable, and we can have a hyperplane separating these two dimensions, right? So this is basically a very high level overview of the kernel trick by which we can use SVM for a non-linear decision boundary. Okay, I hope that was useful, and I hope you enjoyed the SVM lecture. Thank you.